welcome back to the course on econometric modeling. This is module 26. Module 26 is part of univariate time series modeling, where we are first going to deal with ARMA and ARMA processes. So, AR stands for autoregressive processes, MA stands for moving average processes, and ARMA stands for autoregressive moving average processes. There are two modules which would be devoted to these topics, but here in this module I will be primarily dealing with MA processes, that is moving average processes, followed by an introduction to autoregressive processes as well. So, univariate time series models are a class of specifications where one attempts to model and to predict variables using information contained only in their own past values. So, we do not consider any other variable, that is why it is called univariate modeling. And of course, univariate modeling is applicable to my understanding only to time series data, because there we are trying to find out whether the series itself contains information, that the information which could be extracted from its past values or past observations. Univariate time series models are useful when a multivariate model is inappropriate or inapplicable because of a lack of availability of data on relevant variables or availability of data with similar frequency. Because for instance, if we are going for a large scale macroeconomic aggregate model, then it is quite possible that sometimes data, relevant data on some of the variables are not available. Second point is that at times the frequency does not match. For example, if we specifically plan to work with very high frequency data, for instance daily stock prices, then there are very few economic or financial data available which are available at such high frequency. So, as a result of which what we many a times try to do, or at least sometimes it is useful to consider a univariate series only, so that the series itself tries to look back its previous values and we try to find out whether it contains useful information or not. Further, multivariate models could also be inconvenient to use for out of sample forecasting. Out of sample forecast requires, basically depending on the setup, you would actually need information on all the variables for a certain period, which might not be possible, and in that case this would also be inapplicable. And finally, these observations motivate the consideration of univariate or pure time series model, since they do not have any cross section element in them, that is why they could be called pure time series models. A white noise process is one with no discernible structure. So, before I start talking about univariate time series model, it is important to define white noise process. We are already now familiar with white noise processes, but the only difference is that probably we have not used the terminology. So, it is actually a process with no discernible structure. It is defined as the process that fulfills three conditions. The first one is that it has a constant mean. The mean could be mu, the mean could be 0. If the mean is 0, then we call it a zero mean white noise process. The variance is a constant term, a finite and constant variance it must have, that is variance of yt is equal to sigma square, and the covariance between any two observations yt ys is equals to 0. So, covariance yt y is equals to 0 for all t not equal to s, right. So, this is a white noise process. Given this definition, you could understand that so far the way we have defined the population error terms, which is normally distributed with mean 0 and a constant variance sigma square, and we also assume that the covariance between ut and ut minus I for any positive I is equals to 0. Alternatively, you also have probably assumed covariance between ui and uj is equals to 0. Then this actually implies that the error term is actually a white noise process. That is why I say that we are already familiar with white noise processes, but probably we have not used the term white noise process. Now, defining moving average processes, the simplest class of time series model that one could entertain is that of the moving average process. Suppose u t equals 1, 2, 3 and so on be a white noise process with mean 0 and variance constant. Then y t equals mu plus u t plus theta u t minus 1 plus theta 2 u t minus 2 and so on plus theta q u t minus q is a qth order moving average model denoted by MAQ. This can be expressed using the sigma notation, as we are having mu constant here and the rest of the term is actually summed up as I equals 1 to q theta I u t minus I, and we again have this u t separately. A moving average model is simply a linear combination of white noise processes. So, that y t depends on the current and previous values of a white noise disturbance term. This equation could be written or rewritten with the help of lag operator, where L y t is equals to y t minus 1 denotes that y t is lagged 1. Similarly, if I have L square y t, then that means this is y t minus 2. So, this L is called the lag operator, and the power of L basically refers to how many lags are there. In order to show that the ith lag of y t is being taken, that is the value that y t took I period ago, the notation would be L raised to the power y t equals y t minus I. Using the lag operator, the above equation can be written as y t remains the same. I have u t theta I multiplied by L raised to the power I u t minus I. So, if this is I equals to 1, then we have L raised to the power 1 and theta u and u t minus 1 plus u t. So, this is the usual thing that we have. Ideally, we should have u t only here, because the moment I have I equals 1, then L raised to the power I u t refers to L 1 u t, which is u t minus 1. Similarly, L square u t is u t minus 2 and so on, or as y t equals mu plus theta L u t, right. So, this expression theta L is basically this polynomial, which is theta I L raised to the power I summed over I equals 1 to q. Okay. In some books, the lag operator is denoted by B, and this is also called the backshift operator. In the subsequent discussions, the constant is dropped from the equation. This constant mu is dropped from the equation to ease out the complexity of the algebra involved without any loss of generality. So, now we consider first of all an MA2 process. So, MA2 process is written as y t equals u t plus theta 1 u t minus 1 plus theta 2 u t minus 2, where u t is a 0 mean white noise process with constant variance as stated above. Now, that would lead to expected value of y t is basically expected value of this expression, and that is equals to 0 for all t, because expected value of u t is equals to 0. Now, consider variance of y t. So, variance of y t would be expected value of y t multiplied by y t, because expected value of y t is equals to 0, which is ideally variance of y t is expected value of y t minus expected value of y t, then y t expected value minus expected value of y t. Since this is equals to 0, this is equals to 0, we are left with only expected value of y t multiplied by expected value of y t. Then we actually substitute y t with this expression. What we are left with? First of all, u t square, then we have u t theta 1 square into u t minus 1 square, theta 2 square into u t minus 2 square, and then there will be all cross products, right. So, all the cross products are here, which I have not mentioned separately, and the reason is that expected value of all cross products is equal to 0, because UT is a white noise process. So, that is why the current and the previous observations are not correlated with each other. So, because covariance UT US equals to 0 for all t not equal to S, all the cross products are 0, as a result of which variance of YT, which is denoted by gamma naught, is actually sigma square multiplied by 1 plus theta 1 square plus theta 2 square. This comes straight from the fact that this is variance of expected value of UT square is variance of UT, which is sigma square. This is also sigma square, this is also sigma square. So, by taking out sigma square, we have 1 plus theta 1 square plus theta 2 square. So, you can understand, if we would have considered an MAQ process, then the variance would have been sigma square into 1 plus theta 1 square plus theta 2 square plus theta 3 square and so on up to plus theta q square. Now, we consider, so for an MAQ process, this is the variance. Now, we consider auto covariance. Now, auto covariance at lag 1 of the series YT and not UT. So, the auto covariance at lag 1 is denoted by gamma 1. So, you can see that gamma 0 refers to basically auto covariance at 0 lag, which is equivalent to the variance. Now, auto covariance at lag 1 is gamma 1, which is again this expression, this is equals to 0, this is equals to 0. So, what I am left with is expected value of YT multiplied by YT minus 1. Now, again I substitute YT and YT minus 1 with their respective equations, and what we have is, first of all, again I am going to drop out all the cross products. So, UT will be only having cross products with UT minus 1, UT minus 2, and when you take expected value, all of them are 0. Next, what we have, theta 1 multiplied by UT minus 1 square, then the rest are cross products, theta 2, theta 1, UT minus 2 square, and rest all are cross products. So, finally, what we have is sigma square multiplied by theta 1 plus theta 1 theta 2. Similarly, gamma 2, we have started with an MA2 process. So, similarly, gamma 2, that is expected value YT minus 2, again I replace them with their expression in terms of UTs or their moving average processes, and what I am left with is all, first of all, cross products, only theta 2 UT2 square is there. So, gamma 2, that is the covariance between YT and YT minus 2 is theta 2 gamma square, theta 2 sigma square, and gamma 3, that is the covariance between YT and YT minus 2 is going to be 0, because you can see that if I have YT minus 3 here, then all of them will be cross products and there will be no squared term. So, this is equals to 0. We have considered an MA2 process. So, for an MA2 process, any higher order covariances are actually all 0. Gamma S is equals to 0 for all S greater than 2 for an MA2 process, and gamma S equals to gamma theta S plus 1 theta 1 multiplied by sigma square for S less than equal to 2. Generalizing for an MAQ process, you would observe that gamma S, where S measures the lag length, that we are considering autocovariance between YT and YT minus 1. So, gamma S is theta S plus 1 theta 1 plus theta S plus 2 theta 2 and so on up to theta q minus S sigma square for S equals 1 2 to q for an MAQ process, and it is equals to 0 otherwise for any lag length which is greater than the order of the process, that is q. Now, we consider the autocorrelations for the MA2 process. The autocorrelation at lag 0 is given by 1, because correlation has covariance divided by the variance. So, covariance and variance both of them are same at lag 0, and that is why this is equals to 1. The autocorrelation at lag 1 is given by gamma 1, that is autocovariance at lag 1 divided by variance. So, this is autocovariance at lag 1, this is variance, and this is what is my tau 1, which measures the autocorrelation. Similarly, the autocorrelation at lag 2 is given by autocovariance at lag 2 divided by again the variance, and this is what we observe. So, for all higher order autocorrelations we have this is equals to 0, because gamma s is equals to 0 for s greater than 2 when we are dealing with an MA2 process. Now, if we plot the autocorrelation functions for a sample MA2 process, suppose that theta 1 takes a value of minus 0.5 and theta 2 takes a value of 0.2. I am just picking up some hypothetical numbers. Substituting these into the formula gives the first two autocorrelation coefficients tau 1 equals to minus 0.476 and tau 2 equals 0.190, right. So, we are substituting the values of theta 1 and theta 2 in these expressions, right, and we are getting these values. So, we know that autocorrelation at lag 0 is equals to 1. So, at lag 0 this is 1. Then at lag 1 we have minus 0.476, this observation. At lag 2 we have 0.190. For any other higher order lags, this is we are having all 0 autocorrelations. So, this is a plot of the autocorrelation functions of an AMA process with the specific values of theta 1 and theta 2. For different values of theta 1 and theta 2, you would be having different patterns of autocorrelations for an MA2 process. The autocorrelation function or ACF appears as shown in this figure. The distinguishing properties of a moving average process of order q are, first of all, expected value of yt equals mu, which is a constant. Variance of yt is equals to gamma naught, like 1 plus theta 1 square plus theta 2 square plus theta q square multiplied by sigma square. We are basically considering an MA process of order q, and this is the expression for covariance for all s up to q. So, less than equal to q, and for s greater than q we have covariance is equals to 0. So, a moving average process has constant mean, constant variance, and autocovariances may be non-zero up to lag q and will always be 0 thereafter. But one thing that we need to mention or observe here is that an moving average process is actually not estimable in reality, because all your independent variables in a moving average process are the population errors and their lagged terms. Now, how if population errors are not observable, then how am I going to utilize them? But of course, there are statistical packages which are designed to estimate moving average processes. Other than that, moving average processes help us in getting useful information and insights about other related process, for example, an autoregressive process. So, next we are going to discuss or first introduce the autoregressive process. An autoregressive model is one where the current value of a variable y depends upon only the values that the variable took in the previous periods plus an error term. An autoregressive model of order p, denoted as ARP, can be expressed as like this. So, this is a structure you are somewhat familiar with as of now, because we have already discussed autocorrelation, and there we had introduced AR1 models up to ARP models. Now, here UT is a white noise disturbance term. So, UT has a constant mean, constant variance. UT most often has a 0 mean, constant variance, and no autocorrelations. Now, equation 1 can be rewritten again like this, and from there with a lag operator, and finally something like this, where the lag operator has already been explained, and phi l is the lag operator where this is equals to this expression. To explain the implication an AR process has, let us consider an AR1 process such as yt equals mu plus phi yt minus 1 plus ut, where ut follows a normal distribution with 0 mean and constant variance. Suppose we obtain 150 simulated realizations with two alternative values of phi equals 0.4 and phi equals 0.95, and they are plotted against time as shown in the figure. So, you can see that this solid line refers to phi equals 0.4 and this dotted line refers to phi equals 0.95. Now, what it shows is that the modulations or the fluctuations in the series with phi equals 0.95 is more persistent, in the sense when it is going up, it is actually going up for a longer period of time. When it is going down, it is going down also for a longer period of time, right. So, as a result of which the peaks and the troughs are most often more acute compared to a series with phi equals to 0.4, right. So, the diagram shows that the fluctuations in the AR1 series with parameter phi equals 0.95 are much more persistent than those of the AR1 model with phi equals 0.4. This implies that the AR1 models are capable of indicating the persistence of univariate time series. An AR1 process can be converted into an infinite MA process. To show that, let us consider an AR1 process without the mean. So, again we are excluding the mean for the sake of simplicity or to avoid the complexity of calculations. Now, by substituting backward for the lagged values of y's on the right hand side of equation 3, what we obtain? First of all, ut remains there, phi yt minus 1 is replaced with phi ut minus 1, because if I write in a similar fashion, yt minus 1 will be phi yt minus 2 plus ut, right. So, I have phi yt minus 1. So, we have phi square ut minus phi ut minus 1 phi. So, phi ut minus 1 phi square ut minus 2, again ut minus 2 is substituted with its similar expression. So, like phi ut minus 3 plus ut minus 2 and so on. So, this process will continue. We have ut equals 1 plus phi L plus phi square L square plus and so on, again in terms of lag operator, and this is an infinite GP series which can be summed up as 1 upon 1 minus phi L. So, finally, we have ut upon 1 minus phi L. This moving average representation for y is convergent if and only if mod value phi is less than 1, because if mod value of phi is actually greater than 1, then you can see that the denominator will be okay. First of all, by convergent we mean that if I look at this series instead of this expression, you can see that if mod value phi is greater than 1, then as time goes back, the value of phi square is actually keeps on increasing, phi square, phi cube, 5 raised to the power 4. So, even if phi is a negative number, then as we go back, then the modulations will be like of greater dimensions around the axis. If phi is a positive number, then also we will be having phi probably going up, or the series is actually going upward, right. So, as a result of which, this is actually, in order to have the series convergent, we must have mod value of phi less than 1. This is called the condition for covariance stationary of the AR1 series. Alternatively, this condition states that the inverse of the root of the autoregressive lag operator polynomial be less than 1 in absolute value. Inverse of the polynomial root of the autoregressive lag operator. So, you can see that the polynomial lag operator is 1 minus phi L, and its root is, this implies that this is equals to 0, implies that L is equals to 1 by 5. Phi, so this is the root, its inverse is phi, and the inverse of this root should be less than 1 in absolute value, which is equivalent to this condition. In module 24, we derived the variance of an AR1 process, where this was the AR1 process, this was the variance, and where sigma square was the variance of this term. Similarly, the AR1 model described in equation 3 will have variance equals to sigma square 1 minus phi square, where sigma square is the variance of ut. So, simply by drawing analogy we are doing this because we have already proved it, and here ut is a white noise process very similar to ET in this context. To find the autocovariances of lag tau, we multiply both sides of the AR1 process of equation 3. So, this was my equation 3, which is simply an AR1 process. So, we multiply both sides of it by y t minus tau. So, y t minus tau, y t minus tau, y t minus tau. For tau greater than 1, we have expected value of y t minus tau. Phi comes out, again we take expected value, we denote it by gamma tau, and this is actually equal to phi y t minus tau, because we are denoting it by gamma tau is the covariance between y t and y t minus t. The lag is of t. The lag between y t minus 1 and y t minus tau is tau minus 1. So, that is denoted by gamma tau minus 1, and this is equals to 0, and that is why we simply have phi multiplied by gamma tau minus 1. This is called the Yule-Walker equation. Since it is a recursive equation, it helps us to determine the entire autocovariance sequence if gamma 0 is known to us. Now, we know that gamma 0 is equal to the variance of y t, which is equal to sigma square upon 1 minus phi square. Just now we have drawn it or derived it. So, gamma 1 will be phi multiplied by the gamma related to the previous observation. So, gamma 0. So, we have phi multiplied by sigma 1 minus phi square. Similarly, gamma 2 will be phi square multiplied by gamma 1, which is phi sigma square 1 minus phi square. So, sigma square into 1 minus phi square and so on multiplied by phi square. Now, generalizing, we have gamma tau equals phi raised to the power tau sigma square upon 1 minus phi square. So, this is valid for all tau equals to 0, 1, 2 and so on. Dividing the autocovariances by gamma naught gives us the autocorrelation as rho tau. We are denoting the autocorrelation here by rho tau, where tau refers to the lag between the two observations, and this is equal to phi tau for all the tau equals 0, 1, 2 and so on. You can simply see that this is my denominator always variance, that is gamma naught, and the correlation, that is rho tau, will be having gamma tau divided by gamma naught. So, all this gamma tau will be having this variance component. So, this cancels out and what I am left with is equal to phi raised to the power tau. So, that is how the correlation is phi tau, phi raised to the power tau. Note that the autocorrelations gradually decay, which is typical of an AR1 process. If phi is positive, the autocorrelation decay is one sided. So, it decays like this. The autocorrelation function would look like this. If phi is negative, the decay involves back and forth oscillation. So, if phi is negative, then the decay would be something like this. Okay. But of course, what we need is that phi to be less than 1, because if phi is greater than 1, then we will not have decay and we will not have convergent series. The general pth order AR process, as shown in equation 2 and in its lag operator form, this is like this, where L is the lag operator, phi L equals 1 minus phi 1 L minus phi 2 L square and so on, minus phi p L raised to the power p is covariant stationary if and only if inverse of all roots of the polynomial lag operator phi L lie inside the unit circle. So far we are dealing with AR1 model, then we gave some examples with AR2 model. Now, talking about ARP model, which has already been introduced, and we are just now trying to talk about what makes a pth order AR process convergent or covariant stationary. So, the requirement is that all the roots of this polynomial lag operator should lie inside, or inverse of all the roots of this polynomial lag operator should lie inside the unit circle. Alternatively, all the roots of this polynomial lag operator should lie outside the unit circle. So, that was about ARP process, just an introduction. We will continue more with the ARP process, its derivation of its further characteristics, and then with ARMA process, that is autoregressive moving average processes, in the next module. These are the references I have consulted. Thank you.